Thanks, Tomer. Liron David is PhD student at Tel Aviv University. She obtained her BSc in Electrical Engineering and Electronics and Computer Science at Tel Aviv University in 2011. She completed her MSc in Electrical Engineering Department at Tel Aviv University in 2014. Now she is a PhD student at the Electrical Engineering Department under the supervision of Professor Avishai Wool at Tel Aviv University. She got Rector's Award. She got a Rector's Award at Excellence in Teaching the academic year 2015 to 2016, and got in 2017 Weinstein Award for Excellence in Studies.
Okay, hi everyone, good afternoon. So I want to tell you about a talk that I was given in RSA in last February. This is a joint work with Professor Avishai Wool. And what we did is we present an algorithm that finds the key after a side channel attacks. So in order to understand that, let's first of all see what is an encryption algorithm. So an encryption algorithm is a process that receives as an input a readable message and a secret key, and output a non-readable message. Now the whole idea with encryption algorithm is that if you don't know the key, you cannot decrypt the message. Now, eventually, every encryption algorithm is implemented on a physical device. And every physical device leaks information from side channel attacks. For example, it has power consumption, electromagnetic radiation, timing information, sound, and so on. Now, an attacker can use all this information in order to find the secret key of the encryption device. So how does it work? So most of the side channel attacks that are known in the literature are based on divide and conquer, which means, first of all, the attacker divides the full key, which is not known, into some sub-keys, and then given the leakage, he obtains some information about each sub-key. And then what he done, he combined all this information together in order to find the secret key. He does this by enumerating over the full key. So what we did is actually we developed an algorithm which is a key enumeration. So what is a key enumeration problem? So let's say that we assume that we have the independent sub-key sizes, each one of them of size n, and each one of the probability, we also have the corresponding probability distribution of each one of them, which means that for each sub-key candidate, we have the probability that this candidate is the correct sub-key candidate. Now, what we want to enumerate over the full key subspaces from the most likely to the least likely. So there is an algorithm that enumerates all the full keys, but the problem with that algorithm is that the space complexity is very high, is n to the power d over 2, which means that at some point the algorithm stops because it will exceed the available memory. Now, what we did is we did a new key enumeration algorithm that uses bounded space, which means much, much less space complexity. So in order to explain our algorithm, what I'm going to do is I'm going, first of all, to show you how the optimal order works that takes much memory, because we are going to use that in our algorithm. So the optimal algorithm works as follows. Let's say that we have a graphical representation. We have two sub-keys. We have key 1 and key 2. Now let's say that I want to enumerate over all full keys that are composed by the two keys, key 1 and key 2. So if we look at the graphical representation, every n rows are correspond to the value of key 1, and the n column are corresponding to the values of key 2. Now, if we look at intersection I of row I and column J, if we look at the area of this rectangle, so the probability of this rectangle corresponds to the probability of the key 1 at position I and key 2 at position J. Now, the goal of this algorithm is to output compartments by decreasing order of the area. So in order to do that, they maintain a set, they call it F in order to specify frontier, and this set contains potential next candidate. Now what they did is as follows. In each step they extract the most likely candidate in F, and they then insert its successor. Now, a very important observation they made in their algorithm is that this set frontier contains at most one element in each row and in each column, so that the size of this frontier is bounded by the length of the dimensions. So now what we did here is if we have only 2 subcases, but what happens if we have more than 2 subcases? If we need to combine more than 2 subcases. So for do that, they applied a recursive decomposition, which means that for each 2 subcases list of size L, they merge together into one list of size L squared. So if you just summarize the optimal one takes a lot of memory, which means that the memory grows quickly and then exceeds the available memory, which is not good, it's not feasible. So what we did, we showed in the last RSA conference, we presented a new algorithm which has bounded space complexity, and more particular, it takes d squared w plus dn for some design parameter w which can be tuned. So how our algorithm works? So we need to bound the space, right? Because we want bounded space. So we bounded the space in 2 steps. First of all, we bounded the set, the frontier set, and then we bounded the length of the list themselves. So in order to bound the frontier set, what we did is we divided the key space into layers of size W. Then we applied the optimal algorithm within each layer. So we started with the first layer, and then if we didn't find the key that we was looking for, we continued to the next layer. And if we didn't find, so then we continue to the next layer, and so on. As we can clearly see, and we showed it in the paper, the size of the set, of the frontier set, is bounded by 2 times W. Now, the second thing that we wanted to do is we wanted to bound the length of the list themselves. To do that, we divided each one of the W layers into squares of size W on W. So then the enumeration within each layer was square by square. So then it works like this. If, for example, we start with the first layer, which is itself a square, and if we don't find the key that we were looking for, then we continue to the next layer. But now we're going to do it square by square, which means we start with the 2 square at the edges that contains the most probability candidate. And then when we finish with 1 square, we continue to the next square, and so on. And then if we finish to go over all the layer, we move on to the next layer. Again, we start with the 2 edges squares that contains the most highly candidate. And when we finish with 1, we continue to the next one, and so on till we finish one in this layer, and then we move on to the next layer. As we can clearly see from that picture, all what we need to store in order to be able to enumerate this algorithm is only 2 squares of size W on W, which means we need a space of W, and that's it. Now, again, if you can see here, this is an enumeration of 2 subkeys. If we want to enumerate more than 2 subkeys, so we need to apply a recursive construction. So then we have this formulation, this recurrence formulation, and if we solve it, we get d squared W, which together with the input, we get d squared W plus dn. Okay, now in order to show you that our algorithm has very good performance, in addition to that it has bounded space, we made some simulation. We chose 2 values for W. One is n, and the second is 2 to the power 25. And we chose that value because when we chose that value, the space complexity is about 1 gigabyte. Okay, so now if we look at that picture, at this graph, we can see 2 important things. First of all, if we look at the rank of 2 to the power of 33, we see that beyond that rank, the key cannot enumerate anymore, this algorithm. That's why he just fails because of inefficient memory. While our algorithm continues and continues and will never stop till he finds the correct key. The second thing that we can see is that the running time of our algorithm is very close to the running time of the optimal one. And if we look, for example, on the space consumption, we can also very clearly see that our algorithm for those values is bounded, while their algorithm, the optimal one, grows and grows till it just explodes because it just exceeds the available memory. And if we also look at the ranks, we can see clearly that our algorithm is very close, the ranks of our algorithm very close to the rank of the optimal one. So if we can just look at our algorithm, we see that we have very, very good performance that are very close to the optimal one. In addition to that, we have a bounded space which we can enumerate many keys. Okay, so if you just conclude what we did. So we presented a bounded space key enumeration, which can be tuned to use the available RAM. And this is very important, because now the attack can enumerate over large numbers of keys without never exceeding the available memory. And that's it. Thank you.